So we want to look at a couple more examples with diffraction. We're going to look at a graphical question, and then we're also just going to look at one that's not graphical. It involves using the dark fringes and all that. We'll kind of see how you do the theories around that, how to set those ones up. So we have a student, they're going to set up a double slit apparatus to examine the angle of diffraction between the central maximum and the first order maximum. They're going to vary the wavelength of the light source. So let's look at what we have on our axes. So we have sine of the angle of diffraction. So up here we're going to have sine of theta. And then down here we're going to have the angle of diffraction. Or sorry, we have the wavelength. Now, using graphical analysis, we want to determine the separation distance d between the slits. So we have sine of theta, we have lambda. We're told we're dealing with the first order maximum, so we're dealing with bright fringes, and we're dealing with n equals 1. In order to deal with this, we need an equation. So the equation that's going to help us out with this is going to be lambda equals d sine theta over n. But we said that whenever we have an equation, we want to isolate for what's on our y-axis. In this case, sine of theta is on the y-axis. So we want to get sine of theta by itself. Well, if we rearrange for that, so we're going to isolate for y. If we isolate for y, we're going to get sine of theta is equal to n lambda over d. And then the last thing we want to do is separate out the x variable. So we're going to separate out the x variable. So we're going to get sine of theta is equal to this n over d times lambda. Because now you'll start to see we have some equation in the form of y, which is, our sine of theta, equals this slope times x, and then plus b. But in this case, we're just going to say b is 0, theoretically. So if I plot this y variable versus x, or if I plot sine of theta versus wavelength, the slope of that line is going to give me this n over d, or this fringe order divided by this distance between the slits. So what we know is we know that the slope is equal to n over d. Now, we could also say that d is just n divided by the slope. But in this case, we know that n equals 1. We're told we're dealing with the first order fringe. So really what we know is that d is just going to be 1 over the slope. Now someone might ask, why are you writing out the word slope instead of m? Isn't that shorter? Yes, but a lot of times when we do graphical analysis, mass is there fairly often, and I don't want to mix up m for slope and m for mass, so I just write out the word slope. Maybe I should use the letter g for gradient, but it is what it is. So to find the distance between the slits using graphical analysis, I need to take the slope of the graph and I need to invert that. Well, let's go up to our graph here. Now, if I look at my graph, I have these 5 points. I have a line of best fit that's been constructed. I've extended the line of best fit and I've extrapolated it. Probably not the correct thing to do because extrapolation is always a little bit dangerous. But nonetheless, we're just going to assume the trend follows that linear structure. So we need to identify 2 points on that line of best fit. Oh, let's see what we can look at. So this point here looks like it's pretty easily identifiable. So I'm going to mark it with an X. And I'm going to say, well, that looks like it's about 210 nanometers. And then this point here is about 0.1200. A little further along, well, this point near the end, this also looks very easily identifiable. So this is the point 740 nanometers, and then this point is 0.4100. So I have an x, and I have an x1, y1, and I have an x2, y2. So I could certainly mark that x1, y1, x2, y2. So we're going to find the slope of this line of best fit. So my slope, we get this y2 minus y1 over x2 minus x1. And again, be mindful that the y-axis, the units are nanometers. So up top, and I'm going to convert that to meters actually. So I have this 0.4100 minus 0.1200. And then in the denominator, I have 740 nanometers, or 7.40 times 10 to the minus 7 meters, minus this 2.10 times 10 to the minus 7 meters. Just because at the end of the day, I want to keep everything in meters. And most likely on a diploma exam, how this is going to work out is it's going to say something along the lines of the separation distance d expressed in scientific notation is a dot bc times 10 to the minus d meters. That's most likely what you're going to see. So let's see what we get here for the slope. So if I'm really careful and I do my best here, I'm going to get that the slope, it's going to be a big number. It's going to be about 5.472 times 10 to the 5 meters inverse. Because again, those meters are in the bottom, so when I write the units, I'm going to say meters inverse. So I have a slope, and I know that the diffraction grade, the spacing between my slits is 1 over that slope. So the last thing to do is we're going to put that into the slope. So we're going to put that into our equation. So we know that d is just going to be 1 over, and then our slope here, this 5.472 times 10 to the 5 meters inverse. So we invert that, we're going to get about 1.83 times 10 to the minus 6 meters. So based on graphical analysis, I'm going to find that the distance between my slits is about 1.83 times 10 to the minus 6 meters. When we're looking at distance between the slits, things like 10 to the minus 6, 10 to the minus 5 meters, those are pretty good orders of magnitude to be looking for. So I'm pretty happy with this. Again, as we said, for graphical analysis questions, you do have to be given a tolerance for answers, because if you pick a different point, you'll get a slightly different slope, which is going to affect your d value. So we'll usually find the exact answer by like math or like computational means, and then we'll say as long as a student's within a few percent of that, give them the mark.